Okay.
Okay, we are recording now.
Hello.
Chapter 17.
Yeah. Uh, just for the record, if you scroll up a little bit, you see that we are on officially now on part 3 of the book.
Yeah, this is the last sprint. And this is the one with the most amount of chapters. Cool. Okay, so chapter 17 is more like a recap slash a few tiny bits. A few tiny
Yeah.
bits.
Yeah, wrapping up loose ends and connecting them together with the things that were defined after we were first introduced to them, right?
Yeah, so the whole rationale behind this is because the next topic is going to be adjunctions, which we plan to cover today as well, which are defined in terms of isomorphisms of home sets. So home sets, again, it's basically a set that has morphisms between two source destination things. Um, and this is going to matter because adjunctions is a way to get around the equality problem. To get around the equality problem. Yeah.
Yeah, if you don't think equality is a problem, you either need to learn more mathematics or learn more programming because it is a problem.
Even metaphysically speaking. So what is the criteria that we're going to use to say the two things are equal?
Yeah,
Why?
yeah, that way lies endless complications.
Yeah, so there are many ways to define equality of things. And we have to. It's apparently it's complicated to define what is the best way in general, in a general case. So we're gonna try to not talk about that and talk about something else. uh,
Avoiding your problems like a pro.
avoid your problems like a pro. hmm So the first topic is functors. So in Haskell, that's the functor type class, which revolves around fmath contract. As we know, functors map objects, but also morphisms. Um, that's basically like we've seen this before. So the target of one morphism must be equal to the source of the other if they are to be composed. We know this already. If you want the composition of morphisms to be mapped to the composition of the lifted morphisms, the mapping of their endpoints is pretty much determined. Yeah, so that basically means that if you have two morphisms in a category that you are composing, in which the source of one is the destination of the other, the same must be applied when you lift their composition. So that's basically what that means.
Yep.
That makes a lot of sense. And now we go back to the commuting diagrams because they tell us something which is very interesting. So in particular, commuting diagrams form the basis of almost all universal constructions. So what is a universal construction? It is when you just take into account the morphisms between any type of object and you identify some properties such as the initial object and the terminal object, products, co-limits, limits, exponential, free monoids, all of those things. You are just looking at the morphisms of the objects and how they are and seeing some patterns on them, and that's the universal construction. So here we have a product. We've seen this before.
Yep.
We've seen this before. So actually, we have the definition. We pick two objects A and B to see if there exists an object C together with a pair of morphisms P and Q that has the universal property of being their product. And this involves talking about factorizations and all that stuff. We've seen this before, and so on. And it's a special case of a limit. I also remember this. I have very little memory of limits and co-limits. But I do remember that they generalize products and co-products. I do remember that.
Yep.
I also remember these cones when we were talking about limits, and there were some commuting diagrams in there. Commutativity of those diagrams may be replaced with a suitable neutrality condition for the mappings of functors. This way, commutativity is reduced to the role of the assembly language of the higher level language of network transformations. That's kind of weird. This is in the same. thing, the same phrase as this. That's kind of.
No, it makes total sense. What are you talking about? I guess I'm more used to thinking about things in terms of programming language theory, so it's not weird to me at all to hear assembly language and natural transformation in the same phrase. It's just, well, I do
Actually,
admit that it is unusual.
it is weird because one thing is like very low level and the other thing is very high level. But commutativity is playing the role of the assembly language of natural transformations, which is kind of interesting. Then we have natural transformations, which is basically saying that if you have this type of thing, you need to be able to commute those things. That means that if you go here and actually go here and then here, uh, actually here and here, it's the same as doing this and here and here. That's the
Yep.
naturality condition. We talked about this before. Yeah, this is cool. This is very cool.
I really like this diagram.
It's the same sort of. Well, that's actually kind of interesting. When Edu was explaining functors to me back in the day, he was using sheets of paper to explain them to me.
Oh, that's nice.
But the sheets of paper are different in here because Edu was saying that you have the realm of values and things, and then you have the realm or the plane of existence of lifted things, and then the functor is the way that you go from one realm to the other realm. This thing is kind of different because a natural transformation is actually a multiversal interpretation, right?
Yep.
Because you have the values, and then you have one lift and another lift, and in fact you can even bridge the lifts. So that's a natural transformation for you.
Yeah, I really like this diagram. It's very aesthetically pleasing, at least to me.
You are a very simple man.
Am I?
Hmm.
I guess I
There
am.
was a thing. Oh, this one. The action of a functor modifies the content of a container without changing its shape, while a natural transformation repackages the untouched contents with a different container. The order of these
Yeah,
operations doesn't matter. That's what the naturality condition means.
yeah.
That's a very interesting way to put it. Uh, we've seen the Cohn's definition of a limit replaced by natural transformations. A limit is defined in terms of mapping between cones. I will remember that. These conditions too may be replaced by naturality. You may recall that the universal cone or the limit is defined as a natural transformation between the contravariant Hom functor. Um, so the Hom functor is mapping objects to pairs, right?
The home functor is mapping objects to pairs. Well, no, actually, it's the functor that maps an object to a home set, actually.
Yeah, yeah. I forgot to say that it is a functor because it is in the name. But yeah, this is a home set. That makes it. Yeah, that is a home set. And they also contravariant functor maps objects in C to cones, which they themselves are natural transformations. Here, delta C is the constant functor, and D is the functor that defines the diagram in C. Both functors f and g have well-defined actions on morphisms in C. It so happens that this particular natural transformation between f and g is an isomorphism. Yeah, so I believe we've seen this before when we were talking about limits and all that stuff. Again, I have very little recollection of that.
Yeah, it's been a while.
Um, So here's the main point. A natural isomorphism, which is a natural transformation whose every component is reversible. It's the category theory's way of saying that two things are the same. So this is our equality. We are trying. We are. This is the specification of equality, right? A component of such transformation must be an isomorphism between objects. A morphism has the inverse. If you visualize functor images as sheets, a natural isomorphism is a one-to-one invertible mapping between those sheets. That makes sense.
Yeah.
Uh, that makes total sense. So now let's go to home sets. Um, okay, so then we talk about morphisms. They have two ends, unlike objects. If you fix the source and target and the target objects, the morphisms between the two form a boring set, at least for locally small categories. We can give elements of the set names like f or g to distinguish one from the other. But what is it really that makes them different? So what is the difference between two morphisms? So at first glance, you may say they're targeting source destination objects. But now you have a problem.
Yeah.
What if you fix them? So both morphisms go from the same source and the same target to the same targets. Now what is the difference between them?
The difference is how they behave when they are composed with other morphisms later.
Yeah, if there is a morphism H whose composition with F is different than with H, like this, basically, then we can directly observe the difference between F and G. So there is a third party component to equality of morphisms. You cannot judge them different every time. Sometimes you're gonna have to have a third party H in the mix.
Yeah, this reminds me a lot actually of the a compiler writer's view of equality, which is called operational equality in the literature, which means is there any way in a given language to distinguish between two things by a sequence of operations, essentially? In this case, the sequence of operations that you are using to distinguish the two things is composition with a separate morphism, essentially.
Yeah. But even if the difference is not directly observable, we might use functors to zoom in on the home set. The functor f
Oh,
may map the two morphisms to distinct morphisms. So,
hello, Commander.
hello, commander. We know that this may happen, right? If you lift the f and the g with the capital F functor, you may map them to distinct morphisms. That's what this means. In a richer category where the built-in home sets provide more resolution, uh, okay, so this is actually an even crazier scenario in which the targets are the same. You lift them, they are still the same. So then you need a third party on their lifted versions to say that they are different. Where H is not in the image of F, of course, because if it was, this composition would be kind of like ineffective.
Yeah, if H was in the image of F, we would just go back to the case above, right?
Yeah. hmm hmm So home set isomorphisms. Yeah, this is actually very interesting because we know that home set is just a set, right? So it's a set of morphisms. That's what we have in there. But if you have a plain isomorphisms between two home sets, that doesn't tell you much, if anything, because if they are finite sets and you know that they are isomorphic, what does that mean? That means that they have the same number of elements. Cool. If they are infinite, the cardinality must be the same. But any meaningful isomorphism of home sets must take into account composition. Um, so we need to define isomorphisms that span whole collections of home sets, and we need to impose some compatibility conditions that interoperate with composition. And a natural isomorphism fits the bill exactly. So what is that? Okay, so now this is very dense again, but I think we got this. So neutrality is a property of mapping between functors. We know this, not sets. So we are really talking about a natural isomorphism between home set valued functors. So what is a home set valued functor? Is a functor in which the destination is a home set.
Yep.
These functors are more than just set valued functors. Their actual homomorphism is induced by the appropriate home functors. Morphisms are canonically mapped by home functors using either pre or post composition, depending on the covariance of the functor. Um, cool. And then we have the Oneda lemma as an example of such isomorphism. It maps home sets in C to home sets in the functor category, and it's natural.
Very natural.
And this is going to be a pun that even the author will say, I can't get enough of this. One functor in the Yoneda embedding is the home functor in C, and the other maps objects to sets of natural transformations between home sets. Yeah, this is this is very non-trivial stuff. Uh,
Indeed.
so let's
It's
go over it again, at least this last paragraph, because I think it's a lot to cover here. So the Yoneda embedding, it maps home sets in C, right? So sets of morphisms between objects in the C category to home sets in the functor category. So uh, what would that be? The home set in the functor category. We've seen this before, right?
a home set in the functor category.
Is that the
Uh,
target? Is that the target of the functor? I believe so,
home
right?
sets in the functor category. Well, the functor category is the category of functors, and
Yeah.
there are natural transformations between them
Mm-hmm.
as the morphisms.
Mm-hmm.
So basically, it maps morphisms in C to
Natural
natural
transformations.
transformations.
Yeah, that's it. That's it. One functor in the embedding is the home functor in C, and the other maps objects to sets of natural transformations between home sets. Wait. Okay, so one is the home functor in C. We know this already because that's what the home functor does. But and the other maps objects to sets of natural transformations between home sets. Objects to set of natural transformations. Well, yeah, that must be the case, right? Because the home set of a functor category is sets of natural transformations.
Yeah,
Cool.
it is.
Okay. The definition of a limit is also a natural isomorphism. Again, I have very little collection of limits, unfortunately. It's been a while, like 10 chapters ago. Um, yeah, we're gonna see this again later on about the expressing the exponential object using a natural isomorphism between home sets. Okay, and now we have a symmetry of home sets. I think I remember reading this and it was very okay. So before going to adjunctions, because that's the next point, home sets are in general not symmetric. And that kind of makes sense because, again, source and destination, that's what it matters. So a home set
Yeah.
CAB is very often very different from the home set CBA, of course, because you may not have the same amount. Well, if they are the same, they are reversible, right? That's kind of what it means, I guess.
Not necessarily.
Oh yeah, you may have more. That's possible. You may have more, even if the ones that are common between them are reversible.
Yeah.
Mm-hmm. So the ultimate demonstration of this asymmetry is a partial order view as a category, and we've seen this before at least twice. In a partial order, a morphism from A to B exists if and only if A is less than or equal to B. Again, we've seen this before. If A and B are different, then there can be no morphisms going the other way from B to A. Yeah. So if the home set CAB is non-empty, which in this case means it is singleton, which again we've seen this before, then BA must be empty. I think it's because of it's anti-symmetric, right? Anti-symmetric or something.
Yeah, unless A equals B. Uh,
Unless A equals B. Well, because the partial order that we're using is A less than or equal to B.
yeah.
A preorder, which is based on a relation that's not necessarily antisymmetric, is also mostly direction, except for occasional cycles. It's convenient to think of an arbitrary category as a generalization of a preorder. A preorder is a thin category. All home sets are neither singletons or empties, which we've seen before. We can visualize the general category as a thick preorder. I don't know what this means yet. How can you generalize any category to be preorder? You know?
It's the other way around. You can generalize a pre-order to get a category because
Oh, in that case, oh, I read this wrong. That's basically it. You were right. But we did this before, right? I think we did in chapter, I don't know, many chapters ago. We defined the pre-order category.
we did.
Yeah, so that definitely possible.
And it turned out to have very few errors actually,
Mm-hmm.
compared to like set or whatever other categories we've seen.
Well, it's because it must be, or the home sets between the things are either empty or singleton, right?
Yeah, very few errors.
Mm-hmm. Mm-hmm. Cool. So now we go to the very cool stuff. This is the very cool stuff. Uh, yeah. So as we said in the beginning, equality is hard. Equality, saying that two things are equal is kind of hard because how can we say that a criteria to judge them as equal or different is better than another one? That's a problem. Especially
Yeah,
in this book, because in this book we explored a lot of trying to judge and make a reasonable criteria to judge if something is better than something else. That's how we got to the home functor of Haskell being the reader and all that stuff.
yeah,
Hmm. So we're not gonna do that. Like Marinho said, we're gonna run from it. But we still need a way to compare stuff.
yeah,
So that's what we're gonna make. We're gonna make adjunctions to fill that role. So then the chapter starts by talking about isomorphisms again, because it's saying that although a tuple of a boolean and a char and a char and a boolean, they are different. They are equal up to isomorphism because you can just apply an operation to make them equal, which is in this case a swap. And then we're gonna go to adjunction, which in my opinion, I don't know about you, Marin, but this is chapter 18. I think chapter 10 and chapter 15 and 16 was way harder than this one. Way
yeah.
harder.
This is like yeah, this is not that difficult after the road we walked to get here. Um,
Yeah,
but it is interesting. It is very interesting.
yeah.
I like this chapter.
I know it's very intuitive to even to me, and so that's props to the author. So what do we want to say? We want to be able to say that two categories are isomorphic. So how are we gonna say that? What's gonna be the criteria to say that? We're gonna say that they are isomorphic if there exists a functor R from C to D, which is invertible. In other words, there exists another functor L from D back to C, which when composed with R is equal to the identity functor. So this is kind of this is something else because we're not composing morphisms anymore. We are composing functors.
But functors are just morphisms in the category of categories.
Yeah. But yeah, but that's kind of like I know that. But so there are two possible compositions: uh, R after L or L after R. And the two possible identity functors, one from in C, another one in D. So this is the drawing. Very okay, right? So this is like we've seen this in like chapter 1, but instead of the balls are objects, and now they are not objects. They are
Yeah,
they are categories which they can be objects in the category of categories.
as above, so below.
What does it mean that for two functors to be equal? So that's the kind of the question that we are trying to get around because this is equality, and as we said in the beginning, equality is non-trivial stuff. But
It's
this
also a
is
bit. Yeah, it's also too strict sometimes. The book mentions this a few paragraphs back.
Yeah, it says here, the strictness is equality.
Yeah,
Um, okay, so this is what we are basically like drafting. Like the draft is basically saying that if you do R after you have done L, so LR, this is the same thing as being done this arrow here. This is what is written, and the other one is analogous. Um,
it's symmetric, in fact.
yeah, it's very symmetric. But as the book says, uh, uh, yeah. So here's the catch. This is category theory. We cannot look into the objects, so we don't have a general notion to be able to see that the two objects are equal in an arbitrary category. And why do we care about the object's equality? Because two functors when acting on equal objects should produce equal objects. Like this would be a reasonable first step. Um, and then there is a rabbit hole here, which is that if you really want to talk about what equality really is, there is this part, well, this area of computer science slash programming languages called homo. How do you pronounce this?
Homotopy type theory.
Homotopy type theory, which I heard before people talking about it, but I have no clue what that is. I just know it is very hard because when people are talking about it, they talk about very hard stuff.
I mean, it is about equality. What did you expect?
You might argue that functors are morphisms in the category of categories. Well, that's what Marinho said, so it must be true. And indeed, as long as we're talking about small categories where objects form a set, we can indeed use the equality of elements of a set to compare objects. Well, that's because we have the privilege, right? In which where the objects form a set. But remember,
Which
and actually I have to backtrack the book to remember this. Cat, which is the category of categories, is a true category, which means that we have one morphisms and two morphisms. The one morphisms are functors, and the two morphisms are natural transformations.
uh, yeah, basically two morphisms. They use one morphisms as their objects.
Yeah. Um, in cat, it's more natural to consider natural isomorphisms as substitutes for equality when talking about functors. Because how are we going to say that well, we're establishing that because of this fact that we have one morphisms and two morphisms, which means that we must talk about natural transformations. We're going to make as a reasonable assumption that the two functors to be quote equal, they need to be natural isomorphic. Yeah. So we're going to talk about equivalence instead of equality then. And then two categories C and D are equivalent if you can find two functors back and forth between them whose composition is naturally isomorphic to the identity functor. So what does that mean? That means that if you compose the two functors, and actually this is actually a two-way thing, equivalence, because it's saying here, it's a two-way. Uh, so this thing and this thing, they're gonna compose to something, and they are isomorphic to the identity functor. So that will be equivalence. In other words, there is a two-way natural transformation between the composition this and the identity functor that, and this and that. We, and this is cool, and this is would be very powerful to do, but we're not going to do that. We're going to do adjunction, which is weaker than equivalence. So we are stepping things out. We are being humble, right? So we say equality is cool, but that's very hard. Equivalence is cool, but that's also hard. So let's go adjunction. That's weaker but good enough. And why is it weaker? Because it doesn't require to be a two-way thing. Um, no, actually, not only that. It's because it doesn't require that the composition of the two functors be isomorphic to the identity functor. And instead, it stipulates that it's a one-way natural transformation from this to this. So there is an arrow here. That's not an equal sign. That's very important. Uh, so you can go from the identity of the D category to the composition of the two functors. And, well,
You
these,
can
these
go
are natural
from
transformations, right?
yeah, you can go from the composition of the other way around to the identity of the other category, but you
Yeah.
can't go in the other direction. That's like yeah, that would put us back in the isomorphism territory, and we're not gonna do that.
Wait, what would put us back into the isomorphism category?
Like if the two arrows could be flipped, then we are right back to isomorphism between the
Ah,
two, right?
yeah. That's very
Yeah.
true. Okay, so we're gonna call. I don't know the name. I don't know. I don't remember the Greek names, bro. Bruh. But these are Greek letters.
I think those are eta and sigma, but I might be mistaken.
Okay, but this one we're gonna call unit, and the other one we're gonna call co-unit of the adjunction. Notice the
Be-
asymmetry between these two definitions. In general, we don't have the remaining mappings, which is what Marinho just said, because if we had them, that means that we went all the way back to equivalence again.
yeah.
So we don't have these. We don't have these. Because of this asymmetry, the functor L is called left adjoint to the functor R, while the functor R is the right adjoint to L.
And of
Uh,
course, that only makes sense if you draw your diagrams in a particular way.
no risk of error, no risk of confusion.
Indeed.
The compact notation for the adjunction is this. To better understand the adjunction, let's analyze the unit and co-unit in more detail. So this is basically what we're talking about. So let's start with the unit, right? It says, so we're talking about unit. We're talking about this one
Is
here.
the one above, yeah.
Yeah, so it's a natural transformation, of course, because we're going from the identity functor to a composition of two functors, which is a functor. Because functors do make a category. It's a natural transformation, so it's a family of morphisms. Uh, yes, yes. Given an object D in D, the component of eta is a morphism between ID, which is equal to D. Well, it's the identity functor of lifting D, which is equal to D in this case.
Well,
And
by definition, it is, right?
by definition it is. And this functor lifting D, which in the picture is called D prime. And why is it D prime? Because if you have D and you lift using L to this point, and then you apply you lift that with R back to D, which is what
you
is happening
may,
here.
yeah, you may not necessarily end up in the same place exactly.
Yeah, we're gonna go to D prime. We're gonna go to D prime, and we're gonna make eta applied. I think it's component, right? The network transformation terminology.
Yeah, it's the component at D.
The
Um,
component of eta at D. That's the type signature. And noticed that the composition R after L is an end functor in D. Oh, L, yes, because you ended up in D again.
yeah.
This equation tells us that we can pick any object in D as a starting point, and we use the round trip functor R after L to pick our target object D prime. Then we shoot an arrow uh, eta with the component D to our target. And then this is basically it's analogous, right? So it's the same thing.
Yeah, not quite actually, because we're going the other way, right? We start with the targets of the co-unit instead of the source.
Well, uh, okay, it's not analogous, it's symmetric, I guess. That's the way to put it. Because we start with C, then if you lift using R, you go to this point on the right. And then if you lift again, you go to L. And then we're establishing that there is a way to go from C prime to C using sigma at component C. It tells us that we can pick any object C in C as our target and use the round trip functor, the same thing, well, symmetric as before. Then we shoot an arrow from the source to the target. Another way of looking at the unit and co-unit is that unit let us introduce the composition, and the reason of that verb is because the composition goes at the target of this,
Yep.
and the co-unit eliminate the composition, because if you just look at this, what are you doing? You are removing stuff. There is C here, and there's C here, and there's this here, and there isn't that here.
Yes.
I don't know how helpful that is. I think the
Oh, it is
diagrams speak
actually.
for themselves.
Yeah, the diagrams speak for themselves, but this is also very helpful because this notion of introduction and elimination, it has to do with it actually relates very profoundly with pattern matching actually.
We're gonna have to you're gonna have to teach me that later then, because
Well,
I don't see the connection between yet this and pattern matching.
well, basically, when you construct a data type, that's like introduction of
Ah,
you're introducing an operation onto a value, and then when you pattern match on the results of that, you are eliminating that operation from the value.
ah, that is very profound. That is very profound. Okay, that leads to some obvious consistency conditions which make sure that the introduction followed by elimination doesn't change anything. So what are we saying with this? We are saying that well, we are basically doing equational reasoning again. So if you have L composed after L after identity of D, and you replace D with the definition of eta, you're gonna get this. And then if you replace this with this, which is the identity of C, right?
After L, yeah.
After L, you're gonna get L again. You're gonna get L again. Uh, but that's kind of sus,
Why?
because we are using like this step is using what.
There's
Oh no, we are
a
using what we have. I thought we were using the forbidden stuff, not
yeah. No, we're using what we have. It's just associativity,
yeah, yeah, yeah.
basically.
And the same applies to R. These are called triangular identities because they make the following diagrams commute. Yeah, that's basically what we're seeing here. Okay, cool. These diagrams, these are diagrams in the functor category. The arrows are network transformations, we know that, and the composition is the horizontal composition of network transformations, which I remember that. I remember that from back in the day. Then we can make these things, and funnily enough, uh, apparently, I was not expecting that, to be honest. R Peer is the introduction, and return by well, it's a warning if you make return and peer different in Haskell. Um, and I believe they plan to make this warning like default. And the co-unit is extract, right?
That's from co-monads, which
I never used them. I use this one a lot, like many times, but I actually don't know. I never used this one. Very, very freaking interesting. Here M is the end of functor corresponding to this, and W is the other end of functor. This is going to be apparently this is going to be part of the definitions of monad and comonad later on, which is very cool. Um, well, this is now the interpretation as containers, which we get it, right? The return is basically wrapping, and the extract is unwrapping. That's cool.
yeah.
Uh, we'll see later that every pair of adjoint functors defines a monad and a comonad. I'm very excited to see that, because I never seen functors being the way to define a
I
monad and a
mean,
comonad.
I
I'm very
mean,
excited for that.
every monad is an applicative functor, right? You know that.
I know that.
But every applicative functor is a functor.
Yeah, yeah, yeah. I know that as well. but
But that
we're
means
gonna
that
jump.
every moment
But we're
is
gonna
a
jump
functor.
apparently. Yeah, no, but we're gonna jump apparently. We're gonna go all the way from a pair of adjoint functors, jump the applicative, and go all the way to monods and comonods.
Yeah.
I never seen that. Well, this one is kind of obvious because of what you said. Uh, yeah, in Haskell we use those a lot. We can, however, define adjunctions of endofructose in Haskell. Here's the part of the definition taken from this package, which I actually never used before. I never used adjunctions in Haskell, by the way. I should say that.
I really like the choice of letters here.
F and E, F and U.
Yeah.
The definition requires some explanations. So, well, a Haskell explanation. So what are we saying here? We are describing that this class adjunction has some constraints. In the case that f needs to be a functor and u must be representable, which we're going to talk about it later.
Yep.
Still today though. And those are constraints. And after the vertical bar, we specify functional dependencies, which I never used in Haskell, by the way. I never made a type class that had functional dependencies. So we are saying here, we are saying that given an f, you can make a u. That's what is written here. And the other thing is also true. Um, the other thing is also true. So now we're going to go to adjunctions and home sets. So now we know what is an adjunction. We know what it is in Haskell, and we know what it is in the mental model. So what's basically the justification is we are kind of dumb and we cannot do equality either neither equivalence. So let's do this instead. That's good enough for our purposes. That's more than good enough. And this is how Haskell does it. And now we're going to go to adjunctions and home sets. So, what is important to mention in here? Blah blah blah. Okay, I think I'm gonna have to read most of it because this part is very foundational. It's very important.
I
So
really like the next diagram. I looked at it a lot actually.
there is an equivalent definition of adjunction in terms of natural isomorphisms of home sets. So this definition ties nicely with the universal constructions. Every time you hear the statement that there is some unique morphism which factorizes some construction, you should think of as a mapping of some set to a home set. So we say this a lot when we talk about products, co-products, limits, co-limits, all that stuff. We usually say the term factorization. Usually.
Usually.
You should think of as yeah. So the factorization can be often described in terms of natural transformations. And the reason is because it involves commuting diagrams. That's the reason. A natural transformation maps morphisms to commuting diagrams. So in an universal construction, we go from a morphism to a commuting diagram and then to a unique morphism. That's usually the pattern. That is true. It can be a sheet of paper, it can be a cone, it doesn't really matter. But that's usually what happens. We end up with a mapping from morphism to morphism and from one home set to another. If the mapping is invertible, and if it can be naturally extended across all home sets, we have an adjunction. So this is very non-trivial stuff. We're going to see an example later on. The main difference between universal constructions and adjunctions is that the latter are defined globally for all home sets. For instance, using a universal construction, you can define a product of two select objects, even if it doesn't exist for any pair of objects in that category.
Any other pair. You missed a word there.
Any other pair of objects in that category. Oh, that is important. For any other pair. Now it makes sense. As we see soon, if the product of any pair of objects exists, we can define it through an adjunction. So adjunction seems more powerful than an universal construction.
Yes, but also less precise.
That is fair to say. So here's the alternative definition. We have two functors, L, D to C, R, C to D. No problem. We can pick two arbitrary objects, the source object D in D and the target object C in C. No problem at all. We can map the source object D using D to C using L. So what are we doing? We are picking D, we're picking
Going
D,
left.
and then we are
Yeah.
applying L, the functor L. So we're going to LD, which is, again, we are going to C category now because we traverse the L bridge. Now we have two objects, LD, which is this one, and C. They define a home set. Yeah, so these are all the possible morphisms between this guy and this guy.
Yep.
We can do the same thing about with the other guy. So D and RC using R. We can do the same. We say that L is left adjoint to R if there is, if and only if, there is an isomorphism of home sets. So what you're basically saying is they form an adjunction if there is an isomorphism between the set of these morphisms and this set of morphisms.
Yep.
And why is this a universal construction-like definition? Because you're only using the morphisms to describe the stuff. That's why.
And it
Uh,
must be natural in both D and C. That's also important.
that is natural in both C and the D and C.
Yeah, that's literally the next line.
No, I know that is the next slide, money, but I'm trying to figure out why. Why it needs to be natural in both D and C. Oh, it's written here. Naturality means that the source D can be varied smoothly across D and the target C across C. We have a natural transformation. I don't remember this one as well.
That's
Between
phi or phi, depending on how you want to pronounce the I.
between the following two covariant functors from C to set. Here's the action of these functors on objects. So why does it need to be natural on both D and C, Marin? Did you get that?
Because they are arbitrary objects. Like, they are not fixed exactly. Like,
Go on.
we are varying. D is like it can be any object in the
I
category
agree.
D,
Yes, and C the same.
and C the same. And in order for those to actually be arbitrary objects, and for those to be natural transformations, if they are not natural transformations, then the composition kind of doesn't work because
Wait,
then you
there's
are.
no natural transformations being mentioned here. We have a functor, we have objects. That's it. Then we have home sets.
Uh,
Oh, okay, I see. The neutrality condition is to make sure that the commutativity diagram here makes sense.
yeah,
I see
yeah,
the problem. I see the problem. So the reason is because we need to be able to make sure that if you do this and then this and then this is the same as doing this and all the other possibilities.
yeah. For
That's it.
whatever, yeah, for whatever morphism you pick in one of the home sets, yeah, you need to be able to commute with
Hmm.
the option of going the long way around through the other category.
Yeah. I see. More precisely, we have a natural transformation phi between the following two covariant functors from C to set. Here's the action of these functions on objects. So this is a natural transformation because this is going from a C to from the category C to a home set. The other natural transformation psi acts between the following contravariant functors, which is the other way around, right? So it's from D to this thing and from D to this thing.
Yeah,
And they must be invertible as well. It's easy to show that the two definitions of the adjunction are equivalent. For instance, let's derive the unit transformation started from the isomorphism of a home set. So this is what we established earlier. Since the isomorphism works for any object C, right? That's one of the things. If we know it's natural up to C, D and C, D and C can be whatever. D and C can be whatever.
Yeah.
Universal construction powers. Um, it must work for C equals to LD. So what if you collapse these two things into the same thing, right? What does
Yeah,
that mean?
we're going. I find it pretty neat that we do this trick so we can exploit the fact that the identity must exist, essentially.
Yeah. Going all back to the drawing board, identity must exist. Going back to the Greeks. So we're gonna have this thing, we're gonna have this home set that can be whatever, but we know a fact from it, which is that the identity must be there. That's basically what it means. The natural transformation will map this morphism to an element, this, right? So what is this element? This is a home set
Yep.
in the D category of all the morphisms going between D and the composition of functors on D.
Yep.
Or inserting the identity functor I, a morphism in, boom. And now you have a natural transformation. You know that there, because now this is a functor, I is a functor, this is a functor, right? And this is
Uh,
picking a particular object. In this case, we are just lifting a particular D, but D can be arbitrary.
yeah.
Um, so we get a family of morphisms. They form a natural transformation between the functor I and this, like I said, and this is actually eta. So what have we concluded? We have concluded that the two ways of defining an adjunction, both using a universal construction methodology and using this other thing, which is these commuting diagrams, they are equivalent. They
Not
are,
equal.
yeah. You can map things from one to the definitions of one to the definitions of the second.
But they're not equal. They're just equal up to isomorphism
Yeah,
or
yeah,
equivalent.
yeah.
Uh,
So conversely, starting from a unit to unit, we can define the transformations between home sets. And then we're going to do the other way around, right? We're going to do the other way around.
yeah.
So I don't know. I don't know. We have 10 minutes. I think we should. This is fine. Like,
I think, yeah, no, I think we're okay.
this is basically explaining like the some pieces of how you do the other way around, right? How do you show that from one you can derive the other? Um, and now we go back to Haskell here, which is the definition of the adjunction. So apparently, in this type class, you have these two things, left adjunct and right adjunct, which are basically mimicking the phi and psi natural transformations. The equivalence between unit and co-unit formulation and the left adjunct, right adjunct formulation is in these mappings. So you can derive one way using the other way, as expected. Um,
Yeah.
uh, okay, so now we're going to talk about why this is a representable functor. We're going to talk about it. Because remember, in the definition of here, we say that the U needs to be representable. That's what the type class is saying, is telling us. Cool. Um, the reason for this is that to the first approximation, we can treat the category of Haskell type as the category of sets. When the right category D is set, the right adjoint R is a function from C to set. Such a functor is representable, and we've seen this before, although another chapter that I have to reread at some point.
Yeah.
If we can find an object rep in C such that the home functor is naturally isomorphic to R. It turns out that if R is the right adjoint of some functor L from set to C, if R is the right adjoint, such an object always exists. It's the image of the singleton set unit under L. Uh, yeah, I was expecting. Marin, did you grasp this with intuition at all? Because again, I think I really need to reread the representable functors things.
Let's see. If R is the right adjoint of some functor L,
Yeah, from set to C. Because you're assuming that D is set.
Such an object always exists. It's the image of the singleton set under L.
And which object? The rep object, such that the home set between rep and anything else is naturally isomorphic to R.
The home functor, in fact.
Yeah, the home functor. I said the home set, sorry.
Uh, well, the right category is set, which means, okay.
The
Oh,
left,
but L,
go
the
ahead.
thing is, L exists, right?
Sure.
That implies that there is some object which is the source on the other side, right? In set.
Wait, that implies that there is a source object in set?
Yes, because set in this case is D, right?
Yeah, that makes sense. That makes sense. Okay, go on.
And it's the image of the singleton set. Why the singleton set, though?
Turns out that if R is the right adjoint of some functor L from set to C, we are saying that rep is L applied to unit.
Oh, because unit is the terminal object, right?
Sure. Why? Even if that's the case, why must be unit here in this case? Like it's I don't follow how if this is true. Like if this is true, how do we know that the object that suffices this condition here is unit?
Uh,
You know?
well, we know that set is non-empty, right?
We know that set
And
is non-empty, yes?
if we do the identity trick to collapse the two objects in D to just a single object, and we know that the identity must exist from that object to itself.
Sure.
What is the if we know that it's non-empty, we know that if we collapse the two objects to be the same, we have an identity, and we also know, in fact, that I'm trying to process this as I'm talking. You can you
No, no,
tell?
that's called brainstorming. But if we understand this, everything else kind of makes sense because what is written in here? This is basically the natural isomorphism that we were talking about before. This is the same thing as this thing. But we know the missing pieces now because we know that D is set. We know that this object is going to be the unit one. Yeah, the unit one. And we also know that D in this case. So that means that we have this thing. For a given C, the right hand side is a set of functions from the singleton set to RC. Yeah, that follows. We've seen earlier that each function picks one element from the set RC. The set of functions is isomorphic to the set RC. Yeah, we also know that. We know that this is isomorphic to just RC. And then if you make the C generic, you're going to have this thing, which shows that R is indeed representable, which again, I'm going to have to revise that at some point. So this particular part of the chapter, I would like for us to go back. Just this part. Like just this. Because we have only two subsections to go to finish.
Yeah, the main thing I'm wondering is why the singleton set and not the empty set?
No, because if it's empty, we're screwed. Because then the functor is unrepresentable. I know the answer to that.
Oh, right, right, right. Because we lose the isomorphism in that case because, well, from absurdity, the empty set, you can get anything, right? Um, any given, yeah, no, any given morphism that comes out of the empty set cannot possibly be isomorphic to another morphism because,
Well, yeah,
oh,
that's kind of
yeah.
yeah. That
Mm.
follows, but again, I still have to process this a little bit better. Okay, so the last two things are products and exponentials. So now that we have this new terminology, now that we know adjunctions, how can we play with it? That's basically the two last subsections. So let's try. So the gist of a universal construction of the product is the ability to factorize any product-like candidate through the universal product. We've seen this before. So here's the definition again. The product of the two objects A and B is the object this, equipped with two morphisms first and second, such that for any other candidate C equipped with these morphisms, there exists a unique one that factorizes P and Q. So this is a lot of stuff. The drawing is not here, unfortunately, but we gone through this already.
Yeah, we saw this a couple times.
Yeah. So as we've seen earlier, in Haskell, you can implement the factorizer that generates this morphism from the two projections. So this is P, this is Q, and this is going to be M.
Yeah.
Is going to be M. So then, how can I do the things? We can use first and second, compose those with the factorizer using P and Q to define P and Q actually.
Well, we get back to P and Q. Yeah.
Yeah. And as we've seen, we have a mapping that takes a pair, P and Q, and produces another morphism M, which is, not surprisingly, the application, well, the result of factorizer.
Yeah.
How can I translate this into a mapping between two home sets that we need to define in an adjunction? The trick is to go outside of the has category and treat the pair of morphisms as a single morphism in the product category. So we're going to start talking about pairs. So Cartesian products, basically. So now we're going to have a reminder. So what is the product category? Take two arbitrary categories. The objects in the product category are pairs of objects, one from C and one from D. The morphisms are pairs of morphisms naturally, one from C and
Very
one from D.
naturally.
Yeah. To define a product, yeah, this type of stuff is like this is like very intuitive. Even if you don't read you read nothing from the book. You just read chapter 1. This paragraph in chapter 18 is still very fine.
Yeah.
To define a product in some category C, we should start with the product category C with C. Um, Pairs of morphisms from C are single morphisms in the product category this. Yeah, so that makes sense given the affirmation definition. It might be a little confusing at first that we are using a product category to define a product. These are,
Yeah.
however, very different products, which is true because
Yeah.
one of them is using universal construction. The other one is straight up like hardcore Cartesian product.
You're literally just gluing two categories together.
Um, and and you're using the same terminology, product for both.
The
Um,
overloading is real.
so we don't need a universal construction to define a product category. That is true. We don't. All we need is the notion of pair of objects and pair of morphisms. That is also true. However, and that's the cool part, a pair of objects from C is not an object in C. That is true. It's an object in a different category, specifically this one. We can write the pair formally as this, where A and B are objects of C. The universal construction, on the other hand, is necessary in order to define the object this, which is an object in the same category C. In the same category C. This
Yeah.
object, Wait a moment. Are we saying that the universal construction is saying that this is an object in C?
Well, yes, because before we were operating just in C, and we used the universal construction to define a product inside of C. So that is the case.
Uh, uh, yes, yes, yes. I got the notation was completely off to me. Now I understand what you. I completely understood what you said. This object is supposed to represent a pair. Is supposed to represent a pair, in a way specified by the universal construction. It doesn't always exist, and even if it exists for some, might not exist for other pairs of objects in C. Um, let's now look at the factorizer as the mapping of home sets. The first home set is in the product category C with C, and the second is only C. A general morphism CC would be a pair of morphisms F and G. Well, that makes sense. But to define a product, we are interested in a special morphism in CC, the pair P and Q, that share the same source object C. That's okay. In the definition of an adjunction, the source of the left home set is not an arbitrary object. It's the result of the left functor L acting on some object from the right category. The functor that fits this bill is the diagonal functor, which I don't remember what it is anymore.
It basically takes an object and doubles it into a pair.
Well, it duplicates it and makes it into a pair.
Yeah.
The left-hand side of the home set in our adjunction should thus be.
This.
I don't know if I'm following this though. Wait a moment. So the object that we are supposed to be creating with universal construction should represent the pair from this other product, this alternate universe.
In this
Um,
other category, yes.
um, it doesn't always exist. What doesn't always exist? The pair?
If you try to construct products by universal construction, they might not exist for an arbitrary pair of things in C. It might exist only for particular pairs of things in C.
Mm. So the first home set in the product category is the product category, and the second one is C. We are looking with adjunction, so we are looking onto equivalence of home sets. The first home set is the product one, the one coming from the Cartesian product of of C category. So this is that.
Yeah.
And the second one is C. That makes sense. We are composing the morphisms because we need a pair of morphisms in order to have morphisms in this category. That makes sense. But to define a product, we are interested in a special morphism, the pair P and Q that share the same source. That share the same source. Share the same source.
Yes.
That's okay. In the definition of an adjunction, the source of the left home set is the result of the left functor acting on some object from the right category. Let's go back. The left home set.
Scroll up all the way to that diagram that I said that I liked. I think that might help.
So the left. No, this is it. It is the application of the L functor to an object of the right category.
Yes.
It's exactly that. It's 100% that. The functor that fits this bill is easy to guess. It's the diagonal functor. It's the diagonal functor. Oh, the L functor.
Yeah.
I see. Whose action object is this. The left-hand side home set in our adjunction should thus be.
No, it's actually delta C, not IC.
Oh, delta C, sorry. It's a home set in the product category. Yes. Its elements are pairs of morphisms. Are pairs of morphisms that we recognize as the arguments. Yeah. CC, AB. Makes sense. The right hand side, home set lives in C. And it goes between the source object C and the result of the R functor acting on the target object CC. Yeah, so if you go all the way up, this is what we're talking about, right? This guy.
Yeah.
So we have a D and we have RC, and the
I
D's
think
gonna
if
be
you
the right.
I think if you scroll down a little bit, there's another diagram.
Yeah, this is the down on the diagram. So it goes between the source object C. Uh, Source object C and the result of applying some functor acting on the object target object in CC. I don't know if that follows though, because D is the not the source category, right? This is the target category object, correct?
Yeah, D is the target.
D is the target. So, but in our case, C is going to be the target because it's the right hand side.
Yeah.
And it goes between the object C and the result of some functor acting. Yeah, I don't follow this at all. Yeah, but it is down here though. That's the functor that maps up the pair AB to the product object AB. Uh, to the product object AB. Oh, I see. I got confused because C in this case is an object of the destination category, which in this case is C.
Yeah.
Okay, I see. So this part follows. The other one is R lifting C. R is a functor that acting on the target object. So it picks a C and it lifts to the pair. Uh-huh. Now let's go to the drawing here. So this is C and this is CC. So if I do delta, that makes sense. If I do the morphism P and Q, I go to AB. That makes sense because this is a product object. And if I apply this is a product functor then.
Yeah.
And if I apply the product functor, I go to AB that lives in C, that I could go through M, but I'm going from CC. I see. We still don't have a full adjunction for that. We first need our factorizer to be invertible. We're building an isomorphism between home sets. The inverse of the factorizer should start from an M, a morphism from some object C. No, what I said before was wrong then. This is the to make it like the reverse of this.
Yeah.
I don't want this. I want to know what is this description. So I was confused correctly, which is kind of nuts. Uh, yeah,
Well,
so the source object is C. The source object is C. That means that C here, C here is the source thing, and this is the destination thing, and this is the left hand side of the home set.
that's not just a plain C though, it's a delta C. You have to keep that in mind.
I will. So this is CC. L is the delta.
Yeah.
D. What
Was
is
called
D?
C in the other.
No, no, no. What is D in the other case? That's what I don't understand.
It's called C in the other case, the lowercase
No,
c.
but D is not the object of the source in the definition.
No, it is actually.
Oh, it is in fact. Oh, I know that my confusion is because the semantics of source and target depends if you're using L or R, and I'm just fucking stupid. Now I see.
No, it's actually delta C.
Terrible, but okay. So in other words, M should be an element of, yeah, that makes sense. The inverse factorizer should map M to a morphism PQ in CC that goes from CC to AB. So the inverse of the factorizer should map M. So what are we doing here? So delta C AB here, right?
Yeah.
In this category, that makes sense. Yep, amorphism PQ. Yeah, so this drawing doesn't help at all for this thing.
No, it does. It kind
No,
of does.
it doesn't. This is 100% about this thing as on the bottom. This is why PQ were introduced here and they are in the drawing. So this is not about the like ongoing way. This is about the reverse way because
No, it's about both of them. You're just looking at the wrong side of the diagram.
I'm just looking at the wrong side. Don't know if I follow that. So okay, so this thing is the home set of delta C, which is this thing, and AB, which is this thing. Agree?
Yes.
Cool. So this is the home set of that. We don't know the home set of the right hand side because it's not showing up for some reason. It's not showing up.
Uh, it is M actually.
It is M. M is not a home set. So I'm waiting for this notation. It's not here. It's written by in English in here. And that's why I got confused. Cool. Ah. Okay. The inverse of the factorizer should start from a morphism M. Yeah, yeah. So these two things are about the inverse. We don't have the pair in the other way around. The normal way, quote. Which is kind of sad. Lives in C and it goes between the source object, C, and the result of the functor R acting on a target object, CC.
Yes, that's the bottom part of the diagram.
So this would be C parenthesis C and delta C.
No, actually, that's
It seems to be the case though. Oh no no no! It's the R functor, so it needs to be this one, the bottom one.
yeah.
So it's gonna be C parenthesis C comma and then this notation here.
No, it's actually the product in C, so it's the
Oh, this one,
notation.
this one.
Yeah, that one.
I see. Jeez. Okay.
No,
Cool.
it's not. It's not in fact the identity in C.
Yeah. Okay, so this is the reverse. If the mapping exists, we conclude that there exists the right adjoint to the diagonal functor. The functor defines a product. That functor. In Haskell, we can always construct the inverse of factorizers by composing M. Yeah, we've seen this already. To complete the proof of the equivalence of the two ways of defining a product, we also need to show that the mapping between home sets is natural in A, B, and C. Well, because of what we discussed earlier. So to summarize what we have done, a categorical product may be defined globally as the right adjoint of the diagonal functor. So what are we saying here? We are saying that this home set is naturally isomorphic to this one,
Yes.
which means that the morphisms. This is a home set of morphisms in the category CC that goes from pairs of C's to pairs AB,
Yes.
and that's naturally isomorphic of all the more of the M's available, which is C to go into the pair.
Yeah,
Well, actually, that's wrong. This is a pair. This is a product.
that is true. Well, they are both products,
No,
except
but
they are products
that's
in
bad.
different
That's just
senses.
bad naming. That's just bad naming. I'm gonna avoid that. So the product is the result of the action of our right joint functor product on the pair. Even the book is using it. Notice that any functor CC is a well, that needs to be the case. So product is a bifunctor. In Haskell, the product bifunctor is written as just tuple. You can apply these two types, and that's not a big deal. Last thing, the exponential BA or the function object this can be defined using a universal construction. We've seen this before. This construction, if it exists for all pairs of objects, can be seen as an adjunction. Again, the trick is to concentrate on the statement. For any object Z with a morphism G, right, there
Right.
is a unique morphism H. So what are we doing here? We have a product from Z with A going to B, which is the type signature of G. We're gonna have a unique H, which is Z going to the function, right? But we should think of them as an exponential anyway.
Should we?
Yeah, that's what we learned, that functions are exponentials. That's way back in the day though. That's not.
I prefer to think of them as functions, actually.
No, but that's not going to be
But
useful because that's the whole purpose of this section. But okay, in this case we are dealing with objects in the same category. So the two adjunct functors are endofunctors. Why are we dealing with objects in the same category?
because a function object is an object in a category, right?
In the category of functions?
No, in a category that may have function objects in it.
I don't follow. Why are we dealing with objects in the same category in this case?
Because if you want to make a product of Z and A, they must be in the same category, right?
Right.
And Z is in fact the function objects that we're interested in. So it must be in the same category as A, otherwise you can't build a product with Z and A.
Ah, okay, that makes sense. Thank you, Marin. So the left L functor, when acting on object Z, produces ZA. So if this is a functor, Z uh, uh, if it's a functor that corresponds to taking a product with some fixed A. I understand that. But how do we know this? How do we know that the L functor is this? It goes from Z to Z and A.
Because if you look up at the signatures of the two morphisms that we're interested in, the one on the right takes Z as the source, and the one on the left takes Z and A as the source.
Oh, so you're talking about these two functions.
Yeah.
So if you take into consideration their type signatures, you're going from the category.
The other way around, G is on the left and H is on the right, and L, which is the functor going left, goes from the source of H to the source of G.
Oh, I was not thinking those terms, bro. Makes sense. So now R, I imagine, is gonna go to B, from B to AB. AB,
It's
functional object, yeah. Again, A is fixed. The adjunction between these two functors is often written as. Then there's this weird notation. Do you know this notation? Do you know how to decipher this?
Uh, Remember when we were using a dash to mean basically a hole
Yeah, yeah,
in a home set to denote a home functor, right?
yeah.
This is basically the same thing, except it's using that as the as holes in a product and an exponential, respectively.
Yeah, but we are defining the L and the R, right? So this should be the L functor and this should be the R functor.
Yes.
So I don't understand. Because this is supposed to be Z then.
Well, it's an arbitrary z, but it pairs it with a fixed a, and that's your functor.
Yeah, but the other one should be BA.
Yeah, it takes an arbitrary b, and the exponential on the top is a fixed a, and it's the same a that's on the left
Yeah,
of
no,
the
but
turnstile.
so the dashes are different, right? This dash is representing an arbitrary thing. Oh, but in that case it makes sense, I guess, because it can
The
be
dash is a
B.
parameter, actually.
Yeah,
You
this
can
could be
think
a
of.
parameter of any sort. But aren't we saying that whatever goes in here as well?
Uh,
I can be mistaken. But if I am mistaken and this can be different, the notation is bad. Do you agree on that?
I mean, they are parameters, so
Yeah, no, but the notation leads me to believe that they are the same because the symbol representing them is the same.
yeah, they are related, but they're not actually the same.
Okay, so no risk of confusion. Strike three.
Yeah, no risk of confusion at all. And Uli joined us. Hello, Uli. And he has no microphone.
The mapping of home sets that
He or
underlies this
she, I don't
adjunction
know.
is
But yeah.
best seen by redrawing the diagram that we use in the universal construction. Yeah, so that's what we were talking about. So we have H, we have G, Z, A, and B. They are all from the same category. So these are all endofunctors.
She actually. Okay.
Cool. And then notice that the evolve morphism, which I remember from chapter 9, but I would have to revise it again, is nothing else but the co-unit of this adjunction. I remember something like that back in the day. This was
Yeah,
way
it's
back.
yeah, it's the Lispy thing, right? Where you have a
Yeah.
pair with a function and a value that is a valid argument, and you evaluate the pair into the results of applying the function.
Yeah. So what are we saying here? It's saying where. So this is a product. This is a product. Oh, we are converting this notation to the new notation. I see. I see. So why is that the case? So L after R on B. Uh, we can't do that though. Do you agree, Marie?
L after R on B.
There's no way to do that. If I do L, I cannot do L after R.
Why not?
Wow, it's written here. It's in the drawing.
L after R.
On B, right? So you pick B, you lift with R, and then I'm assuming then you're gonna apply. You cannot apply H then because H is the other way around. You see?
I mean, you can unapply it, I guess.
What does that
uh,
mean, dude? What?
let's see. A is fixed.
A is fixed.
A is fixed. A is fixed. What does that imply? That implies that
If a functor has an adjoint, this adjoint is unique up to isomorphism. Well, I guess. Yeah, the other thing doesn't matter, and then we finish the chapter. But how come these things? How come these things? I believe this is function application, remember? I vaguely remember that. We just deconstruct the tuple and apply A to B to this thing and we get the B. It was something like that.
Hmm.
So what does it mean to do L after R on B if we cannot do that? Or am I tripping? We can, and I'm just not following.
I mean, I think we can actually because uh, here's the thing. The L is actually a functor, right?
L is a functor that when you give it an object, it produces the object with A.
Yes. So that means if you start with B and you apply R, you end up with that
This function.
A. Yeah, with the A with the fat with the double arrow going to B.
Yes.
And if you apply L to it, you end up with an A with a double arrow going to B paired with A.
You also yes.
And then you can apply G to get back to B.
Oh, I see what you said. Okay, so what you said ended up in here. Cool. It's exactly what you said. You pick a B, apply R to it. What does that do? That gives you a function. If you p, but that function, let's call it a Z for lols. Uh, L picks a Z and returns the product with A of whatever Z is, which ends up
Yep.
being this, which is kind of yeah. But how can we do the same with the diagram? Like I understand what you said. What you said
The
makes
Z,
sense.
the important point here is that Z and B are arbitrary.
No, I understand that. I'm just saying, can't we conclude the same with the diagram?
Well, yes.
Because you pick a B, you give it an R, you pass through R. R will give you this thing, okay?
Okay.
But there's no arrow that gives me a way to apply L in the diagram. But we can, given that Z is generic.
Z is a variable. Yeah, you can instantiate it to whatever you want.
Yeah, so this diagram doesn't help on that.
It does because it tells you that okay, if you start with a Z and you apply L, you
Oh,
get a
okay,
ZA.
we need to arbitrarily say that our Z is this thing. But there's no arrow. That's why I was confused. There was no arrow in here saying that. But you are right, because for any other object Z, that means that I can just say Z is this just for lols, which means that I go back to here, which is this thing. Cool. Are we done?
I think we are. I think we are.
So I'm gonna stop the recording now.